Hey everybody. Hope everyone's making progress on the reports. I'm trying to get this while I still have some light. Last time was horrible, and last week I just didn't even make an update. It was way too late to get any decent lighting to record, and I had a lot of assignments, so I didn't have anything to really update that was too interesting either. But so this is my update on my senior research on the partially derived nature of the Schrödinger equation. I'm just about done with my research. Only about 20 pages left of this book. I find it interesting that this book, where Fleisch ends, is where the quantum mechanics demystified by McMahon begins. I like it though, because for my project, I want to start with the equation, break it down piece by piece, defining everything needed to be understood first. So my first approach is somewhere in between the middle of these two resources and about the opposite of the book on wave mechanics, but obviously not nearly as detailed as any of them since I'm just writing my senior paper. I'm not writing a book. But basically all you need to understand for the Schrödinger equation is complex variables, partial derivatives, linear algebra, differential equations, eigenfunctions, eigenvalues, eigenstates, trigonometry, a lot of integral calculus. There are different environments and conditions for the equation as well, and for how to use it. For example, there's a time dependence or independence. You can do one-dimensional or multi-dimensional. There's infinite potential or finite potential wells. And for the wells, all that means is that there's zero potential outside of the well or the quantum region of the given particle to exist, or that the potential decays exponentially outside the region, respectively. This relates to why electrons can only exist in their certain energy states, for example. Now, being wave functions, we primarily focus on sinusoidal functions like sine and cosine. Set an operator, the Hermitian, multiply that by the function equal to the imaginary part times the reduced Planck constant times the partial integral of the wave function with respect to time in each dimension. Simple stuff, really. There's a few transformations and relations to know. There's the Euler relation of the exponential function to a sinusoidal function. There's the Laplace transform. We have the Broglie relation, de Broglie, the Fourier transform, and from there, we can deduce things like the Heisenberg uncertainty principle. We can reduce the Gaussian wave packet in position space and momentum space, and more than that even. But then we also have to consider some other nerdy terms like what's Hilbert space, complex conjugates, Dirac notation, the Kronecker delta, and the Dirac delta function. But you will all have to wait till my final presentation to get the deets on those. So home stretch, let's all sail smoothly into our final weeks. See ya.